Welcome to this course on computational mathematics with SageMath. This is 9th lecture on linear programming problems. In this lecture, we are going to look at two-phase simplex method. If you recall, in order to apply simplex method, we require initial basic feasible solution. Now, in case the problem is such where the initial basic feasible solution is easy to guess, we can very easily start simplex method. For example, most of the cases that we have considered where the inequalities are less than equal to type, so we introduce slack variable in each of these constraint, and in that case slack variable can be taken as basic variables and other variables as non-basic variables, and we can start simplex method. However, in many cases, especially when you have greater than equal to inequalities or equal to inequality, starting basic feasible solution is not very easy to guess. So in that case, you may not be able to start the simplex method. So you need some kind of systematic way of deciding initial basic feasible solution. So two-phase simplex method takes care of that. So let us see how we can make use of this two-phase simplex method to solve problems in which initial basic feasible solutions are not very easily available. Right. So in this two-phase simplex method, there are two phases. In phase 1, we introduce some artificial variables and artificial objective function. Basically, we introduce artificial variable to each of the constraint where the basic variable is not easy to guess. For example, all those constraints where it is greater than equal to type or equality type. And also we modify the objective function, we call that as artificial based objective function, and then we solve that problem and find a basic feasible solution with objective function value 0, right? And it would also mean that the artificial variable should go out of the basic solution, or if at all it is there, it should be only with 0 value. Once we have done that, that means we have solved the problem, which is a modified problem. We'll call that as artificial problem with artificial variables and artificial objective function. Then we apply second phase, phase 2. So in first phase, we guess initial basic feasible solution, and once we have the initial basic feasible solution to the original problem, then we apply phase 2 and apply simplex algorithm to solve. That is what is called two-phase simplex method. Now let us start with the standard linear programming problem, which is minimize z is equal to c transpose x subjected to, let us say, ax equal to b, right? So if you have ax equal to b and the initial basic feasible solution is not easily available, then we can apply two-phase simplex method. So what we are going to do, we will introduce one artificial variable, which will be non-negative variable, to each of this equality constraint, right? So that this constraint now will become ax plus y, where y is column vector y1, y2, ym, because we have m constraints. And we look at the objective function, which is minimize y1 plus y2 plus dot 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 ym. That is the now modified problem. You can call this as artificial problem. This y1 to ym are called artificial variables, and this y, which is y1 to ym, is called artificial vector. Now if you have done this, now it is very easy to check that I can take y1, y2, ym as a basic variables for this modified problem. In particular, if I write this 0 comma b, that is, so y1 is equal to b1, y2 equal to b2, dot 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 ym is equal to bm, that gives me basic feasible solution for this artificial problem. Now it turns out that this original linear programming problem has a basic feasible solution if and only if the associated artificial problem that we have defined here has an optimal feasible solution with objective function value 0. This is a theorem, this is a result which is used in order to solve this linear programming problem. Okay, I am not going to prove this result, but what it means is that in case you have solved this problem with objective function value 0, and since the objective function is y1 plus y2 plus ym, and these are all non-negative variables, this w, which is the objective function, will take value 0 if and only if all yi's are 0, or yi's are 0 in though it is not a even if it is a basic variable, but it takes function value 0. Okay, that is what it means. So our first task or the phase 1 will be to solve this artificial problem and get a solution of this, get an optimal solution of this problem with artificial objective function value as 0. In particular, try to push out all the variables y1, y2, ym, which are basic variables to begin with, out of the basic variables. Okay, that is the steps we are going to look at. Once you have solved this problem, then you will have a basic feasible solution of this original linear programming problem, and then you can start the standard simplex method. So let us look at a problem, and then let us employ two-phase simplex method in order to solve. Right. So the problem is this: minimize f, which is equal to 4x1 plus x2 plus x3, subject to 2x1 plus x2 plus 2x3 is equal to 4, and 3x1 plus 3x2 plus x3 is equal to 2. Right. Of course, this problem is very small in size, so we can also find out all the basic feasible solutions, and then we can take one which gives the minimum value. That is brute force method one can always employ. But in case you have a problem involving large number of design variables, then that will not be efficient. Right. So what we are going to do, we will introduce artificial variable with first constraint, that is, let us call that as y1, and with the second constraint y2, and then we will minimize the objective function, which is y1 plus y2. So that is the modified problem or artificial problem. This is the artificial problem which we have to solve. Now in this case, it is quite easy to guess that y1 is equal to 4, y2 is equal to 3, and x1, x2, x3 equal to 0 is a basic feasible solution. So therefore we can start the simplex method. Okay, so let us do the standard simplex method for this problem. Now of course we also need to, the objective function here involves z is equal to y1 plus y2, so both these coefficients are 1. But then this is already non-negative, so this will be an optimal solution in that case. But then you need to actually look at y1 and y2 in terms of x1, x2, x3. So you find out y1 from the first equation, y2 from the second equation, and put it in the objective function that will give you the coefficients of x1, x2, x3, x4. In this case, up to x3. So that is what we need to do. Let us define this problem. So we can define this, the initial basic simplex for this objective function z is equal to y1 plus y2. So of course, as I said, we can find out value of y1 and y2 and from these two equations and substitute in this, and then we can modify these the last row, which is the cost coefficient with respect to the new variables y1, y2, right? So that is cj minus zj. But what we will also do, we will also, in this simplex method, we will also keep track of the original problem, the cost coefficient with for the original problem, that is cj minus fj. F is the objective function of the original problem, and Z is objective function of the modified problem, that is artificial problem. So that is why this row is also taken into consideration. Now what I am going to do is, though I said we can find out value of y1 and y2 from these two equations and put it in the objective function, and that will give me the coefficient, but we will write a small program to achieve that, right? We will call that as artificial update. So what is it going to do? It is going to update this value of y1 and y2 in terms of x1, x2, x3, that is in terms of the remaining variable, and it will modify this the matrix A. That is what it is going to do, right? Similarly, the other steps in the simplex method is going to be the same as before. So we have to do the pivoting, right? We need to find out what is the pivot column, that is incoming variable. Then we also need we need a routine for finding outgoing variable, that is pivot row. Similarly, pivot column and pivoting, all these things we have made use of, right? So these are exactly the same thing. I am just copied those programs here. Now let us start. So we will start this matrix M. I will call this matrix M rather than A, and this will gives me the first 4 rows from this initial matrix. First row, second row, that is with respect to 2 constants. This is with respect to the original objective function, and this is with respect to the modified problem, that is artificial problem. So that's the matrix, including the right hand side. Right hand side here is 4 3 0 0, and that is what you have in this case. Right, now what we will do, we will run this. So first let us create this the matrix, the simplex table. This is the simplex table. That is what exactly I showed here in the earlier case. Now we will update this matrix using this artificial update. Now when we do that, you can see here now the last row, the coefficients has become -5 for x1, -4 for x2, -3 for x3, 0 for y1 and 0 for y2, and the value of the objective function in this case z is equal to -7, right? So that is what we have got. So this is using inbuilt using the routine that we have created. Of course you can manually find out and then write this last row in M. That you can do, right? Okay, now let us, so with respect to this new matrix A, now create the initial basic simplex table. So this is the initial basic simplex table. Now you can see here this objective function row, that is the reduced cost coefficient. In this case they are all negative. In fact, this with respect to or corresponding to the non-basic variable, they are all negative. Therefore this is not an optimal solution. Therefore we need to find outgoing variable and incoming variable. The incoming variable will be decided based on the maximum negative value in the reduced cost coefficient row, which is -5. So x1 will be entering variable, and then look at the ratio of the right hand side by this positive entry in this incoming column. So the first one is 4 by 2, which is 2, 3 by 3, which is 1, and 0 by 4, which is 0. So of course this fj minus cj minus fj we don't have to consider, only these y1 and y2 row we will have to consider. So the minimum ratio is 3 by 3, which is 1. That means y2 will be outgoing. So let us find, using inbuilt function, what will be my incoming variable. So this is 0th variable, that means the first column, right? And then outgoing variable, which is 1, that is the second row, that means y2 is outgoing. Once we have decided incoming and outgoing, then we will pivot M, and once we pivot M, I think there is some problem with this. Okay, let me run again and then see whether it works. This is my M, this is this artificial M, this one, this. Yeah, this seemed to have worked. Now once we have, you can even find out what is my my new M. So this is the new M. You can see here in the first row, in the first column, this pivot element has become 1, remaining all are 0. So that you have to also apply to the objective original problem objective function row. Now let us update the basic variables. Once you have updated the basic variables, you can see here now the y2 has gone out, x1 has entered, and let us prepare the revised simplex table for this. Now again look at this last row, that is reduced cost coefficient row. You have here negative, therefore x3 will be entering. Look at the ratio. So this is negative, we will not have to consider. This is x1, this is 1 by 1, so that is the only, sorry, this one is only one of them. So again x1 will go out, and then sorry, this x3 will be coming in, right? So this x3 is incoming column. So so this is 2 by 4 by 3, this is 1 by 1 by 3. So 2 by 4 by 3 will be 6 by 4. So the y1 will go out and x3 will come in. So again let us update this. So first we decide incoming column, then decide outgoing column row, and then pivot, and then update the variable. All these things we have done, and now let us update the simplex table. So once we update the simplex table, this is what we get. Now you can see here all the entries in the reduced cost coefficient corresponding to non-basic variables have become 0. They are all non-negative, right? And in this case the basic variables now are x1 and x3, right? And y1 and y2 have been pushed out of the basic variables, and the objective function value is 0. Therefore this completes the phase 1. Okay, this completes the phase 1. At this stage, what is the basic feasible solution? x1 is equal to 1 by 2, x3 is equal to 3 by 2 is a basic feasible solution, right? And of course x3 is equal to 0. So x1 is equal to 1 by 2, x3 is equal to 3 by 2, and x3 is equal to 0 is initial basic feasible solution, right? In this case there are only two basic variables are there. So now what we will do, we will get rid of this last row and then the two artificial columns that we have introduced, y1 and y2. Now we will have column x1 corresponding to x1, x2, x3 right hand side, and this row with respect to Cj minus Zj. So we will keep only these rows, remaining we will omit, and we will apply simplex method, that is phase 2, right? So this completes phase 1. Now phase 2, for this we will what we are doing is we are taking the columns of M, and from this we are taking only first column, second column, third column, and the last column, and then we take only the copy of this, but only we take first 3 rows. That is what we are doing. Now this is your modified M. Now again prepare the basic simplex table for phase 1. This is initial simplex table for phase 2, not phase 1, phase 2, right? So therefore now you can see here, now here the reduced cost coefficient with respect to x2 is negative. Therefore again this is not an optimal solution. So we will find out what is the incoming variable and outgoing variable, again using pivot call and pivot row, and then we will pivot and update the basic variables, and then again apply write the simplex table, revised simplex table. Now in this case, actually this should have been here, there is some alignment issue. So here x1 and x, all the values in the last row except this objective function value has become non-negative. Therefore this is optimal solution. What is the optimal solution here? x3 is equal to 2 by 5, sorry, x2 is equal to 2 by 5 and x3 is equal to 9 by 5, and the value of the objective function, the minimum value is going to be 11 by 5. This is negative because we are doing the maximization type, therefore this is the minimum value will be 11 by 5. That is the optimal solution. So this completes the phase 2. So remember what are the things that we have done? We introduced artificial variable and revised wrote the artificial objective function. Then we created the initial simplex table with respect to the revised or artificial problem. Then we updated the objective function row by omitting the artificial variables y1 and y2 in this case, and then we run the standard simplex method. Continue this till you get optimal solution. In case the optimal solution of the artificial problem gives you the solution with artificial objective function value 0, then you have completed the phase 1. And once you complete the phase 1, then get rid of the columns corresponding to artificial variables and also a row corresponding to the artificial objective function, and then run the standard simplex method and complete this till you get optimal solution. That is the phase 2. Okay. Now the same problem we can try to solve using inbuilt function. So let us define A, B, C for this, and then use interactive LP problem. And then if you try to solve this is the problem, exactly the same problem which we have looked at. Now remember here the problem, this objective function, this constraints were equality type. So when you convert into standard form, this will get converted into less than equality. So equality has become 2 inequalities. Therefore, that is why you have a 4 constraints. Right. Now when you run this, of course you can run this step by step using revised simplex method that we have looked at in the last class. But let us just ask for what is P optimal solution. So it says that the optimal solution exists at x1 is equal to 0, x2 is equal to 2 by 5, and x3 is equal to 9 by 5. That's exactly what we got in the last stage of phase 2. x2 is equal to 2 by 5, x3 is equal to 9 by 5, and since x1 is non-basic variable, its value is 0. Right. And what is the optimal value? The optimal value is 11 by 5. That's exactly what we had here. This 11 by 5. Right. Now you could also solve this problem using other methods, like using mixed integer linear program we can solve. So for that you have to create the problem P objective the variable, define that as new variable x with all non-negative variable, and this uses the package glpk, and then set the objective function, add the constraint, 2 constraints. Here they have equality constraint, ask it to show what is the problem it has created, and ask it to solve. So when you solve this, you get the answer 2.2, which is 11 by 5, and the value at which it has solution, that is x1 is equal to 0, x2 is equal to 0.4, and x3 is equal to 1.8. Right. So this is how you solve a linear programming problem using two-phase simplex method, and we apply this whenever you don't have basic feasible solution easily available. Of course, you can apply this to any problem. You can always do with any problem, but wherever the initial basic feasible solution is very easily available, we don't have to do extra efforts or of applying two-phase simplex method. Let us look at one more problem. So let us look at this problem. Maximize this subject to these 3 constraints. Now the constraints are less than equal to, greater than equal to, and greater than equal to. So again, let us convert this problem into standard form first. So that will be minimize negative of z and then subject to these constraints. So in first one is less than equal to, therefore we will introduce x4. Second constraint is greater than equal to, we will introduce surplus variable x5, and the third constraint is again greater than equal to, so we will introduce surplus variable x6. Now x1, x2, x3, and then x4, x5, x6 are non-negative. I should write here x4, x5, x6. Right. Now what we are going to do, so again you can see here, now I can't take, we can take x1 is equal to 40, that is fine, but x5 is equal to minus 10 I can't take in basic feasible solution. Therefore we will have to introduce artificial variables. So we will introduce artificial variable, 2 artificial variables we will introduce, one for the second constraint, one for the third constraint, because first constraint we can take x4 itself as basic variable. Therefore we don't need to actually introduce artificial variable there. You can do that, but it is not needed. Right. So now the problem is minimize y1 plus y2 subject to these constraints. Now again what we will do, we will replace y1, or we will find out y1 and y2 from second and third constraint and write this objective function. So let us do that. When you modify this by substituting value of y1 and y2 from the last two constraints, you get the objective function, which is minimized 20 minus 2x1 plus 5x plus x5 plus x6 subject to these constraints. So this is your now linear programming problem in standard form. So now let us create the matrix, the coefficient matrix, the objective function row, and apply simplex method. Now in this case, actually once you have found out these things, you did not update simplex, update the matrix, right? Remember that is what we did in first case. We found out the modified objective function row for the artificial problem using artificial update. So we don't need to apply that in case we have found out manually. So let us go ahead and do the next step, right? So this is the initial basic simplex table. Again we are keeping track of the objective function of the original problem, that is Cj minus Fj, and this last row which is Cj minus Zj with respect to the modified problem. Okay, right. Now so we will update, we will find out incoming variable and outgoing variables. In this case there are 8 variables, so that is the pivot call. The 8 is number of variables here. So and then 3 is the number of basic variables. So in this case the outgoing variable is going to be x2. The q is going to be x1, that is the incoming variable, and outgoing variable is going to be the minimum ratio, which is this x4, right? So that is, now let us modify the pivot with respect to this entry, which is already 1 here, and then let us modify the basic variables, and then let us write the modified simplex table. So you can see here the first column has become now 0, 1, and all these things are 0. That is the modified simplex table. And you can see here again there is a negative here. So we need to do the next step, that is find out again incoming and outgoing variable and then modify the simplex table. So that is the modified simplex table after 2 stages, right? So now you can see here all the reduced cost coefficients are non-negative. Therefore this finishes the phase 1, and at this stage what you see, the value of the objective function in this case is 40, right, which is not 0, and in this case, although this y1 and y2 have gone out, this y1 and y2 have gone out, and this value here is which 40, that's because in this case x2 x4 are still there in this solution, right? So now we will have to do phase 2 in this case. This completes the phase 1, right? But then the value of the objective function, the artificial objective function is y1 plus y2, which is 0, right? Right? So therefore this completes the phase 1. Now we will do phase 2. That means we will get rid of y1 and y2 column and this last row, and then this is what we get. Once we omit this, we will apply the phase 2. So this is the first step or phase 2, initial simplex table for phase 2. Again here you see there is a negative value, so it is not optimal. So we will find out incoming variable and outgoing variable, and then we do the pivoting and then modify the simplex table. When you modify the simplex table, this is what you get. So now you can see here the last row, that is cost coefficient row, has all the non-negative coefficient. Therefore this is optimal solution, and this solution is given by x1 is equal to 10, x2 is equal to 10, and x3 is equal to 20, and the value of the objective function is 70. So that completes the phase 2. So therefore you have got the solution, x1 is equal to 10, x2 is equal to 10, and x3 is equal to 20, and the objective function value is 70, right? Also notice here that the value of the cost coefficient, there is spelling mistake here, value of the cost coefficient with respect to non-basic variable x5. Here x5 is non-basic variable, right? X5 is non-basic variable. that is 0. Therefore, this problem has an alternate solution. This problem has an alternate solution. Okay, and that can be obtained. We know how to obtain an alternate solution. Now let us try to solve this problem using inbuilt function. So when we define A, B and C and solve this using inbuilt function, in this case what is the solution you are getting? X1 is equal to 30, X2 is equal to 0, X3 is equal to 10. Now if you contrast this with this, the solution which we got X1 equal to 10, X2 equal to 10 and X3 equal to 0. Right? This is different solution. However, the function, objective function value is the same. That is what you see here. There is an alternate solution. So inbuilt function gives you different solution than what we got using simplex table. So that is what I said, there is an alternate solution. Okay, fine. So let us look at, I'll leave you with some exercises. This is the two exercises. So solve these two exercises using two-phase simplex method. So unless you actually require the artificial variable, you need not introduce. You introduce artificial variable when it is needed. Okay, so that is what you need to do. And in case, though I have not taken any example here, but it is possible that you find the phase 1 completes, but then the value of the objective function is non-zero with the value of the artificial variable still in the basic solution. That would be the case where the problem will be infeasible. Okay, so if you have infeasible problem, the phase 1 will, though it will complete, but it will not give you a starting basic feasible solution of the original problem. Okay, so let me stop here. In the next class, we will look at a method which is called Big M method, which will combine simplex method and two-phase simplex method together, and so the phase 1 and phase 2 can be combined together using Big M method. Okay, so let me stop. Thank you very much.